2.1, represent relations and functions. Vocabulary. A relation is a mapping or a pairing of input values and output values. So pairing of input and output. A domain is inputs which we usually use as x's. Range are the outputs, and we usually use those as y's. A function is a relation for which each input has one output. Let's go over here and talk about that a little bit. Probably when you were younger, you had some sort of math program book that had a magic box in here. And they would say if you put a 2 in the magic box, it comes out as a 4. And if you put a 4 in the magic box, it comes out as an 8. And they wanted you to find the pattern, which is, for this, is times 2. So the 2 and the 4 up here are our inputs, which is our domain. And the outputs are 4 and 8. Each input has one output. What you don't want for a function, which is not a function, is if you put in a 2 one time, and it comes out a 4, and you try a 2 again, and next time it comes out a 6. That's something you can't trust. There's no pattern to it. So this is not a function. Equation in two variables. This is an equation that has an independent or input variable and a dependent or output variable. And this output variable depends on the value of the input. This is just a fancy way to say that if I have something like y equals 2x, we have two variables here, and whatever I put in for x, that matters to what I put in for y. So x is our input or independent variable. I can choose anything I want for the x, but because I choose a certain number for the x, then y is set at a certain number. It's dependent output. Linear function. This function can be written as y equals x plus b, where and b are constants, or just plain numbers. You know from Algebra 1 that is our slope and b will be our y-intercept. Okay, representing relations. Relation can be represented in the following ways. You can write them as ordered pairs. You can put them in a table. You can graph them as points, not as lines, but as points. Or you can do a mapping diagram where each input is mapped to an output. Notice that this relation is not a function because it doesn't satisfy the stipulation that every input has its own output. Because if I put in a -2, sometimes I get a +2 out, and sometimes I get a -2 out. You can see that on every part of this way to show relation. This is also the vertical line test for a function. Do you notice I can draw a vertical line through these 2 points? And if I can do that, then this is not a function. In my mapping diagram, I have -2 maps to both outputs. But it's okay to have a relation that's not a function. You just can't flip that around. Function has more rules than a relation. Okay, example 1, identify functions. Tell whether each relation is a function, then explain. On A. Okay, do you see that I have different inputs and they all go to one output? Now, this may be a little confusing right here, but that's okay. I can put in a -1 and get a 0. And I can put in a 3 and get a 0. Just can't go the other way, such as I can put in a -1 one time and get a 0 out, and put in a -1 the next time and get a 5 out. So the first one is a function because each input is mapped into or onto one output. Look at B though. Do you see on B, sometimes I put in the 2 and I get a +2. Sometimes I put in a 2 and I get a 3. This is not a function because the output, 2, is a map both onto 2 and 3. So checkpoint, complete the following exercise. Is this a function, and explain. So go ahead and stop the video, start it again when you're done. Here's the explanation of the vertical line test. So a relation is a function if and only if no vertical lines intersects the graph of the relation at more than one point. So a straight up and down line can't go through the graph twice. How about this, the first one? Do you see it's a function? Because no matter where I draw a vertical line, it only hit that graph once. But this one is not a function because if I draw a vertical line through it in several points, then it'll hit the graph twice. So a good way to figure out if a relation is a function is to graph the points. Example 2, use the vertical line test. Is the equation represented by the graph a function? On A, is that a function? Yes, because it does represent a function because no vertical line intersects the graph at more than one point. On B, look at B. This line goes through 2 points. This line also goes through 2 points. So B is not a function because the vertical lines at 3, x equals 3 and x equals 6, intersect the graph at more than one point. Graphing these equations. To graph them, first you're going to construct a table of values. I usually call this an XY chart. And then plot enough points from the table to represent a pattern. Then connect the points with a straight line or a curve. So example 3, graph this. Step 1, construct a table of values. Now, why did they choose these values for x? They just happen to be easy values to choose from. You would get the same answer if you chose 100 and then a half and 3/16 or whatever for x. They're just not very easy mathematically to put back into the equation. So pick easy x's for you to get y's out. So if I put in -2 for x, I will have y equals -2. Remember to make sure you put in parentheses, minus 2. -2 times -2 is +4. +4 minus 2 is a 2. Now, on -1, so y equals -1 times, -2 times -1 minus 2, +2 minus 2, and that would be 0. And I would keep going and filling in all my points. So at 0, it is -2. At 1, it's -4. And at 2, it's -6. Step 2, plot the points. Notice they all lie on a line. So -2, 1, 2, +2. 0, -1. 0, -2. 1 is -4. And 2 is -6. And then you connect these with a line. Put arrows on both because we know this goes on forever. And let's put this word in here, connect the points with the line. Now if they didn't make a line, then you did something mathematically wrong, because this equation with a plain y and an x that doesn't have any powers, or is not a fraction below the line or anything like that, you know this is always a line. So you don't even have to pick all 5 values for this since you know it's a line. I would definitely pick 3, because 3 you could see if one of them's off. But really, if you were sure of yourself, you'd only need to plot 2 points to draw a line. But 3 is better. Okay, example 4. Tell whether the function is linear. Then evaluate the function when x equals -3. A, is A linear? Yes. Now, a lot of people get confused with this f of x, and that notation is just function notation. It says a function at x equals 6x plus 10. F of x is a fancy way to just write y. So anytime you see f of x, just think y. So is this a line? Yes, because we have a plain x value. So it is linear. Now we're going to evaluate it when it's -3. So keeping the function notation down here, I'm going to say the function at -3 equals 6 times -3 plus 10. And that's -18 plus 10, which would be -8. So I'm going to substitute -3 in for x. All right, on B. Is B a function? No. Because it doesn't have mx plus b form. It has an x squared up there. We'll graph these later. These are quadratic functions. But it is not a linear function. Is it still a function? Yes, but it's not linear. So to evaluate this at negative 3, I'm going to stick a negative 3 in here for each time I see the x. Now, dear Aunt Sally rules say to do the powers first. So negative 3 times negative 3 is positive 9. 2 times positive 9 is 18. 4 times negative 3 is negative 12 minus 1. So we have 18 minus 12, which is 6. 6 minus 1 is 5. Okay, checkpoint. You need to do these 4 checkpoints. On 3, make sure you make an XY box. Choose points that are on the graph. You don't want to choose x is 10, because that point would be somewhere over here, right? And you just don't want to go off the graph. On 4 and 5, go ahead and say whether it's linear, evaluate at negative 1.